Hello, Internet and the AWS serverless community. Hi, my name is Toby Hede. I will be talking today about serverless patterns that have come from using serverless in anger in production as part of my role as head of engineering at Amasim. We're a mobile and energy provider based in Australia, and we use serverless quite extensively. And have complete product, in fact, in the market that is built predominantly on serverless. I'm also the creator of serverlesspatterns.io, and a lot of the patterns you'll see today are actually documented more fully as a design pattern language on that website. So definitely check that out if you're interested in knowing more. So in the beginning was the Lambda. In a serverless architecture, we use Lambda functions to provision services that execute our business logic. Our services should be maintainable, testable, independently deployable, and loosely coupled with other services. So really, function as a web service is the core of everything that we're going to be talking about today. And what I want to stress to you is that your Lambda functions, you will generally expose them as RESTful HTTPS endpoints using the API gateway, and we map the incoming request into the Lambda payload. Now, you can, of course, directly invoke Lambda functions via the SDK, and there are certain situations where that's ideal, but generally recommend putting the API gateway between your caller and the Lambda, because it decouples the implementation. It decouples the client from the implementation. And we'll explore this a little bit more, but it's a really important pattern and the basis of a lot of what we're going to go into. So you'll see this more. Once you have a function exposed as an API, we need to handle incoming requests. And API consumers may unintentionally pass badly formatted data, or you may have bad actors if this is a public endpoint, people deliberately trying to inject bad data, do SQL injection attacks, and all of that kind of stuff that we see online. But you can actually offload a whole lot of work to the gateway and validate inside the gateway using JSON Schema. So in this pattern, you actually define a data model using JSON Schema and validate all of the incoming traffic at the gateway before it even hits the Lambda. The advantages here are it removes repetitive validation logic from the Lambda implementation. So validation code, is this field null? Is it the right length? All of that kind of stuff. It adds a lot of cognitive load to the code as you write it, but it's relatively low value. It's really repetitive. The other advantage of doing this is you avoid invoking the Lambda if the payload is invalid. And it's, you're like, okay, Lambda's probably not the most expensive part, API gateway is, but you're already paying for the gateway call. So by blocking the data, you're avoiding any extra charges. And, particularly if you start connecting to other services downstream, this is really important. So we'll have a look at what JSON Schema is. So the key is in the name. It is a schema for defining properties and objects, and it's in JSON. So there you go. So here's an example. Here's an object that has a hello property and the type is string. So pretty straightforward. And then what would happen is this would be defined in your gateway. The payload here is hello is true, and of course you can immediately see, that's not actually a string, that is now invalid. But here it is, hello world is a string, and so now that payload will be passed through. You can do much more complex things though, and get some quite non-trivial data validation inside your at the gateway level. So here, for example, there's services that is a type of array. The items are all of the string. Here we're saying we need a minimum of one item. they all have to be unique, and we're even saying services is required. So you can build some quite complicated logic inside your at the gateway level, and now you don't need to do a check in the code in the Lambda if length of the array is greater than this or less than that. So it's really handy. Next up, we have the gateway proxy. So the core of this type of development is really tying low-level platform components together with the business logic. And we've seen the API gateway is essential for exposing Lambda functions, but you can actually expose all sorts of AWS services using the API gateway, and either create public endpoints that simply pass through logic, or do proxies. Anyway, you know what I mean. So often you'll see that people are often using Lambda as a glue to connect services. So, you'll take a payload and you'll kind of shape it into the right thing, and here it's hitting into an SQS. But there can be cases where you could drop that Lambda altogether. So connect the API gateway directly to the SQS layer. So again, this is all about reducing the cognitive complexity and the logic. So in this case, we've removed a Lambda from our infrastructure. So there's a cost benefit for doing that, but also we're reducing latency, because that Lambda function, the data is flowing through the API gateway to this intermediary and then onto the SQS queue or the DynamoDB. If you're using Lambda to do validation of data to make sure a public endpoint is passing the right things to the queue, well, we just saw that you can validate at the gateway. So if you're validating at the gateway, that might be the thing that helps you disintermediate Lambda from your architecture. And so now you've got services that are lightweight wrappers around AWS infrastructure. And again, comes back to that first point about decoupling the consumers of the service from the implementation. Maybe this service evolves. Like right now it's SQS, it's very simple, or a simple DynamoDB connection. But now, actually, we're going to need some business logic. We put Lambda in between to do that logic, but because it's a service boundary defined through a RESTful API, we've decoupled the caller. So really handy way of thinking about your infrastructure. The other thing that's interesting in the ecosystem is caching at the gateway. So again, this is a built-in function. Under the covers, it basically just provisions an Elasticache server, and it's just configuration in the API gateway. So again, this is all about reducing latency and cost, and you can cache independently of Lambda provisioning or concurrency because it's handled at the gateway level. And a great way of adding some scale in cases where the Lambda's doing repeated calculations or something that is cacheable. Of course, not all things are cacheable. But the other thing I want you to consider is using a function cache. So this is, it's very easy to forget that the Lambda instance is just a normal container, and you can cache in your code, and we've done that in a few instances. So in this case, you load and cache data inside the Lambda process, and the data might be able to be bundled into your deployed source code, depending on it. We'll explore that in a little bit more detail. But conditions apply here. You really need to think carefully about your use case. So if you are caching data inside the Lambda function and loading that, then the cold start latency, the start time of your Lambda function is going to be increased by however much it takes to load that data. And your cache must also obviously fit inside the memory that's allocated to that Lambda function. So, your mileage may vary. You can't use it as a giant data store because there's a hard limit on Lambda memory. But one interesting thing we see in production is that there's often benefit in turning the memory up because memory and CPU are correlated. So the more memory you have, the more CPU a particular Lambda is going to get, and the more I/O you get. So you might have a lot of memory lying around in some functions because you don't need the memory, you need the CPU. So something to think about. So this is an example from some testing and a thing that we actually were looking at Amasim. And it's easy to forget that computers are actually really good at some things. So we had 100,000, some testing we were doing, 100,000 key value records, 500,000 key value records, like quite long keys. We were trying to replicate a blob of JSON data. So it's not like someone's first name or something. It's a significant amount of data relatively. So 100,000 key values with 100 meg, 500,000 key values, 500 meg of memory. So that's a modest amount of memory. If your customer base in Australia, the reality is, 500,000, 1 million customers is often the ceiling, of companies. Like we just have a smaller population, so it's easy to forget that you can brute force some of this stuff. And then 1 million lookups of 500,000 records was about 200 milliseconds. So that is this kind of code. So this is JavaScript. There's a handler, really basic function. So on line 1, you can see that we're loading some data into a variable called cache. That variable is outside the handler. So it is going to be sort of in the node process that's running. And so each function, each actual invocation of this function can access that. And so you can see on line 5, we're just doing a lookup on that data as a key and then returning. So, you can go a long way doing this kind of stuff. And you see, here's an example of the key value. You know what a function looks like. If that 100 meg of data in a file is not very much, so you might be able to actually put this into S3. We've done some patterns where someone can upload that data into a bucket, and that will package and redeploy the function. That's an interesting idea if the data is, say, infrequently changing or coming from some sort of data source. You can bundle it into the package that gets deployed. But the other thing you can think about doing is actually loading that data from S3. But again, that's going to depend. There's latency costs for loading into that process. So you have to keep that in mind. The next pattern we're going to look at is a really common one in our service architecture, and that's the aggregator. And so the idea in the aggregator is to combine multiple service interactions into a single Lambda function. The intent here is to reduce network communication in our client, reduce the complexity of our client code, and reduce cognitive load, again, by creating abstractions. So if you find you've got a chatty interface with a client, and the common one where you really notice this is a browser client that's doing heavy lifting, that's sort of pulling data from multiple services and then sort of munging it together inside the browser. That's often an indicator that your domain model is not necessarily at the right level, and so you want to pull the code up into a higher abstraction, and that's where this pattern is really handy. So you would put a Lambda the Lambda can handle the interactions, and then the client has less work to do. Queue-based load leveling, or the throttle, is the next one. So the idea with this really is to manage spikes in demand that put pressure on services and can result in a cascade of latency and errors. We use this kind of pattern a lot because our downstream systems, some of our downstream systems have quite limited throughput, and adding a buffer is really, really useful. So in this one, what we do is decouple requests and protect those services using SQS. So instead of invoking a Lambda or invoking a service directly, you push to a queue, and then a Lambda will essentially pull from that queue. You can then control your throughput using Lambda concurrency and batch size to tune and fine tune. So what happens is behind the scenes, you have batch size, which determines how many messages any Lambda function will get from the queue at any point. Now, you don't, as a Lambda implementer, you don't pull the data yourself. There's something in between, some magic in between the SQS and the Lambda that you've written that will just pass the batch size number of messages. And your concurrency then is how many instances you'll have running. So if you've got 10 messages per batch, 10 Lambdas concurrency, it's about 100 per work unit kind of thing. You can actually use this to do very fine grained control. So we have example where it's a single Lambda instance, concurrency of one, pulling a very small batch size because we want to really, really throttle the throughput that goes through to a particularly fragile downstream system. So really powerful way of doing it. One thing that's really worth pointing out, because it catches people out a lot, is you configure the dead letter queue on the source queue. So you can configure a dead letter queue on a Lambda, but that's only used for asynchronous Lambda invocation. If you want a dead letter queue for queue processing, it's actually on SQS itself. Minor point, but worth thinking about. That is the wrong slide. All right. So the final pattern is the event bus. Now, this is hugely powerful, and where I think most people really need to start getting their headspace when doing serverless infrastructure. The good news about the event bus is it's got a lot easier with the advent of Event Bridge. We basically had an implementation using Kinesis and then our own Lambda infrastructure to pull events off the Kinesis stream and funnel them to the right places and manage concurrency and some quite complicated infrastructure. That pretty much is all just irrelevant now. So Event Bridge will do that for you. So Event Bridge takes an incoming event and basically you can connect and coordinate between services using events. So rather than creating that aggregator pattern, you can see this shape here looks a little bit the same. So with the aggregator, you've got a Lambda function that is going, call this service, call that service, do these things. In an event pattern, you just pass the event through into the service and off it goes down into wherever it needs to be. So what you have to do is define a shared event schema. So you need to define and model an event, and it helps decouple the source and the target. You no longer have a synchronous process going on. It's really important to think carefully about events. Events are the API. You need to model events as first-class citizens of your domain, just in the same way that you model a RESTful service and the resources that you have in your infrastructure. a domain event is not the same as a transactional data level event. So you see here is a create order, going off down into some downstream systems. So at the database level, if you're used to a relational database, the order may be multiple tables. So there's a customer, there's an order sort of entity, and the order's made of line items. If you were thinking about your events at that customer order line item entity kind of level, what will happen is the slide will break, but also you're going to end up with this complex state reconstruction that you have to do. So the events come in, and now the customer, the order has come through, but the customer and the line item, we need to stitch all of this back together to get the notion of the order back into all of its parts. And then because we've made our system eventually consistent by going into an evented world, that reconstruction suddenly gets really, really hard. Because, at least in a database, a relational database, those triggers might be within the same transaction context. But now we're getting one entity update, and we don't know where the others are coming from. So you kind of have to wait, etc., etc. So don't do any of this. You need to think upfront about your events and model them correctly and in the right way. It's a real shame these slides are broken. So in summary, use the platform, learn the platform. The validating at the API gateway level is, it's a feature that's just there, and lots of people seem, like the ecosystem is filled with that kind of thing. You need to experiment and prototype to understand behavior, particularly as you start getting into these evented ways of working. That SQSQ thing we experimented with quite extensively. And events are your API. As you move into an evented world, events are the API, and you version and need to think about your events in very structured ways. Running out of time. Thank you. I've been Toby Hede, and I'll be online for questions. Thanks very much.